All right, first of all, in the last lecture, we derived an approximation for this operator for partial u partial x squared plus partial square u partial y squared. We basically approximated that with the large matrix A times the vector u. And it's just the day before yesterday, so it's A is a matrix that has a pretty interesting structure. Does anybody remember what structure A has? Pentadiagonal, right? We have 5 slices. What else? Yes. It's a block matrix. Like each block corresponds to one row of the finite difference discretization, right? Okay, good. So today we're going to talk about how do we solve equations with that operator. So let's first discuss elliptic equations. In the elliptic equation, I'm going to give an example. We want to solve this equation equal to f. With this finite difference operator, we just approximate the left-hand side with A times U, and the right-hand side is the finite difference discretization of f. That trivially converts a differential equation into a matrix equation, right? And how to solve the matrix equation? We can either use MATLAB with a backslash, or when A is so large that a backslash can no longer solve the equation efficiently, we are going to be studying iterative solution methods today. All right. Okay, next let's go to parabolic equations. In a parabolic equation, I'm going to use the example of a heat equation, partial u, partial t. Can you see that? Okay. Is equal to partial square u, partial x squared, plus partial square u, partial y squared. Okay, following the way we solve the 1D heat equation, we are converting this partial differential equation using the matrix A into a what? Ordinary differential equation. Exactly. We are going to convert that into a du vector dt equal to A times u. All right. And the suggested way I would suggest, like when you are working on project 1, you can use OD45 to solve an ordinary differential equation like that. You can either construct the matrix A, or if you can compute A times u without constructing the matrix A, that'll be as good. All right, because that's what OD45 needs. So, and then solve the ODE. All right. Alternatively, in some cases, if the matrix A is very stiff, if you studied ODE, you probably know what stiffness means. It means A has eigenvalues, some eigenvalues that is very large, some eigenvalues that is very small. And if you use the explicit scheme like what OD45 uses, then the time step size you have to use would not be restricted by the accuracy requirement. It'll be restricted by the stability requirement. That is the case where it is much better to use an implicit scheme. Okay, with the implicit scheme, let's say I'm going to give an example of backward Euler. That is u of step k plus 1 minus u of step k divided by delta t equal to A times u at step k plus 1. If this is step k, it would be forward Euler. If it's k plus 1, it's backward Euler. And And if we use a scheme like that, again, we need to solve a matrix equation at every time step. And this is the matrix equation we will need to solve. Just the UK. So I moved all the unknown at step k plus 1 to the left-hand side, all the known onto the right-hand side. And every step, we are going to be solving this matrix equation to advance from step k to step k plus 1. And we keep going. All right, this is two different approaches of solving the ODE. One is use the explicit integration scheme, one is using implicit integration scheme. And in implicit integration scheme, we need to solve matrix equations. And again, we're going to be talking about how to solve this kind of large matrix equations in this very class. Okay, hyperbolic equations. Since I used the red. Hyperbolic equations, again, I'm going to give an example that is the wave equation, partial square u partial t square is equal to partial square u partial x square. This is the equation you are asked to solve in class, in project. And here, I'm going to convert this equation into a first order equation so that we can use things like ODE45 to solve it. Here, I define another variable. V is equal to partial v partial t. All right. Then the derivative. Oh, what did I do? Okay. The derivative of the variables u and v, the discretized variables u and v, would be equal to a matrix times u and v. And the matrix, I'll tell you, it's a block structured matrix. It's a 2 by 2 blocks. Okay. And the blocks would be something like the first row is 0 and I. That is because the first order derivative, oh, this is u. The first order derivative of v is just equal, the first order derivative of u is just equal to v. So the first row of the matrix is 0 and identity, so that when it is multiplied by u and v, it is equal to v. Now somebody tell me what the second row is. What is the second row of the matrix? Yes. A and 0, yes. Great. Because the first order derivative of v is exactly the second order derivative of u, which by this equation is approximated by a times u. Okay, now you have an ODE to solve. You can either solve it using ODE45, like which is what is required in project 1, or maybe you have to solve using an implicit method, like what we have in solving this heat equation. And solving this kind of equation using implicit method is what is going to come in project 2. All right, you'll be solving the same equations, but under a different condition, which makes the matrix very stiff, and you will find it much better to using implicit method to solve it. And that is what we are going to discuss today, is iterative solution methods for solving large linear equations like this one, and like what you're going to see in project 2 when you discretize the wave equation or linearized Euler equation using implicit time-stepping methods. Any questions so far about this? No? All good? Yeah? Why are we starting? Can you ask again? Why did we derive this? Oh, okay. So why don't we just multiply a with u to get the second derivative of u? Okay. The reason is that there is a very good collection of tools to solve ordinary differential equations. That is first order. Right? There are also tools to solve second order ordinary differential equations that involve second order derivatives, but it is nowhere as comprehensive as the tools we have in solving first order ODEs. So if you look at MATLAB, for example, there is a lot of tools for solving first order ODEs. So it is makes our life a lot easier if we can derive a first order ODE instead of a second order ODE when we discretize a PDE. So that is why we convert it into that form. Any other questions?